It's enabled. And I'll deploy a load balance service to it. I'll scale the service and we'll see what happens. First, let's use the GCP console to confirm that the APIs we need are enabled. In the Products and Services menu, we scroll down to APIs and Services. We're looking for the Kubernetes Engine API and the Container Registry API. There's the Kubernetes Engine API. It's enabled. There's Container Registry. It's also enabled. Now we're ready to start a cluster. For this activity, we'll use the command line in the Cloud Shell. For convenience, I'm going to define an environment variable that contains my preferred GCP zone. Now I'll launch a Kubernetes cluster in that zone. The cluster will have 2 nodes. Now the cluster is ready. Let's confirm what version of Kubernetes the cluster is running. It's version 1.8. When you launch a Kubernetes cluster, you may see a newer version. Remember that Kubernetes cluster nodes are compute engine virtual machines. Let's go back to the GCP console and view them. In the Products and Services menu, scroll to Compute Engine and click on VM Instances. There are cluster nodes. We can also view the cluster in the Kubernetes Engine console. The console reports the cluster name, its location, and its size. Now let's return to Cloud Shell. Let's run a web server in our cluster. We've created a Kubernetes deployment called Nginx. The deployment consists of a single pod. Let's confirm that it's running. There's our pod. Now let's expose the deployment we created so that clients from outside Kubernetes can access it. Now let's view the new service. It takes a moment for an external IP address to be assigned. Now an external IP address has been assigned. Let's attempt to visit this IP address using a web browser. We see the Nginx homepage. Our web server, running inside of a Kubernetes deployment, is accessible from the internet. Now let's scale up our deployment. We would do this if load were rising. We name the deployment and specify the new number of replicas. Now let's look at the new number of pods. There are additional pods. Now they're in the running state. Let's also confirm that the external IP address did not change. The external IP address is the same. Let's refresh the home page. We've confirmed that the web server deployment continues to work. In this lab, I created a Kubernetes engine cluster. I deployed a load balance service to it, and we tried a scaling operation, and we saw how seamlessly it worked.
So, we've discussed two GCP products that provide the compute infrastructure for applications, Compute Engine and Kubernetes Engine. What these have in common is that you choose the infrastructure in which your application runs, based on virtual machines for Compute Engine and containers for Kubernetes Engine. But what if you don't want to focus on the infrastructure at all? You just want to focus on your code. That's what App Engine is for. I'll tell you more about it in this module. Let's start with PaaS. Recall that a PaaS is a platform as a service. The App Engine platform manages the hardware and networking infrastructure required to run your code. To deploy an application on App Engine, you just hand App Engine your code, and the App Engine service takes care of the rest. App Engine provides you with the built-in services that many web applications need. No SQL databases, in-memory caching, load balancing, health checks, logging, and a way to authenticate users. You code your application to take advantage of these services, and App Engine provides them. App Engine will scale your application automatically in response to the amount of traffic it receives, so you only pay for those resources you use. There are no servers for you to provision or maintain. That's why App Engine is especially suited for applications where the workload is highly variable or unpredictable, like web applications and mobile backend. App Engine offers two environments, standard and flexible. I'll explain what each is and how to choose. Of the two App Engine environments, standard is the simpler. It offers a simpler deployment experience than the flexible environment and fine-grained autoscaling. Like the standard environment, it also offers a free daily usage quota for the use of some services. What's distinctive about the standard environment, though, is that low utilization applications might be able to run at no charge. Google provides App Engine software development kits in several languages so that you can test your application locally before you upload it to the real App Engine service. The SDKs also provide simple commands for deployment. Now, you may be wondering, But what does my code actually run on? I mean, what exactly is the executable binary? App Engine's term for this kind of binary is the runtime. In App Engine standard environment, you use a runtime provided by Google. We'll see your choices shortly. App Engine standard environment provides runtimes for specific versions of Java, Python, PHP, and Go. The runtimes also include libraries that support App Engine APIs. And for many applications, the standard environment runtimes and libraries may be all you need. If you want to code in another language, standard environment is not right for you. You'll want to consider the flexible environment. The standard environment also enforces restrictions on your code by making it run in a so-called sandbox. That's a software construct that's independent of the hardware, operating system, or physical location of the server it runs on. The sandbox is one of the reasons why App Engine standard environment can scale and manage your application in a very fine-grained way. Like all sandboxes, it imposes some constraints. For example, your application can't write to the local file system. It'll have to write to a database service instead if it needs to make data persistent. Also, all the requests your application receives has a 60-second timeout, and you can't install arbitrary third-party software. If these constraints don't work for you, that would be a reason to choose the flexible environment. Here's a diagram of how you will use App Engine standard environment in practice. You'll develop your application and run a test version of it locally using the App Engine SDK. Then, when you're ready, you'll use the SDK to deploy it. Each App Engine application runs in a GCP project. App Engine automatically provisions server instances and scales and load balances them. Meanwhile, your application can make calls to a variety of services using dedicated APIs. Here are a few examples: a NoSQL data store to make data persistent, caching of that data using memcache, searching, logging, user login, and the ability to launch actions not triggered by direct user requests, like task queues and a task scheduler. Suppose you decided that the restrictions of App Engine standard environment sandbox model don't work for you, but you still want to take advantage of the benefits of App Engine. That's what App Engine flexible environment is for. Instead of the sandbox, App Engine flexible environment lets you specify the container your App Engine runs in. Yes, containers. Your application runs inside Docker containers on Google Compute Engine virtual machines, VMs. App Engine manages these Compute Engine machines for you. They're health checked, healed as necessary, and you get to choose which geographical region they run in. And, critical, backward compatible updates to their operating systems are automatically applied. All this so that you can just focus on your code. App Engine flexible environment apps use standard runtimes, can access App Engine services such as data store, memcache, task queues, and so on. Here's a side-by-side comparison of standard and flexible. Notice that standard environment starts up instances of your application faster, but that you get less access to the infrastructure in which your application runs. For example, flexible environment lets you SSH into the virtual machines on which your application runs. It lets you use local disk for scratch space. It lets you install third-party software, and it lets your application make calls to the network without going through App Engine. On the other hand, standard environments billing can drop to zero for the completely idle application. Because we mentioned App Engine's use of Docker containers, you may be wondering how App Engine compares to Kubernetes Engine. Here's a side-by-side comparison of App Engine with Kubernetes Engine. App Engine standard environment is for people who want the service to take maximum control of their application's deployment and scaling. Kubernetes Engine gives the application owner the full flexibility of Kubernetes. App Engine Flexible Edition is somewhere in between. Also, App Engine environment treats containers as a means to an end, but for Kubernetes Engine, containers are a fundamental organizing principle. I've mentioned application programming interfaces, APIs, several times in this course. Let's be precise about what an API is. A software service's implementation can be complex and changeable. What if, to use that service, other pieces of software had to know internal details about how they worked? That would be a mess. So instead, application developers structure the software they write so that it presents a clean, well-defined interface that abstracts away needless details, and then they document that interface. That's an API. The underlying implementation can change as long as the interface doesn't, and other pieces of software that use the API don't have to know or care. Sometimes you have to change an API, say to add or deprecate a feature. To make this kind of API change cleanly, developers version their APIs. Version 2 of an API might contain calls that version 1 does not. Programs that consume the API can specify the API version that they want to use in their calls. Supporting an API is a very important task, and Google Cloud Platform provides 2 API management tools. They approach related problems in a different way, and each has a particular strength. Suppose you're developing a software service in one of GCP's backends. You'd like to make it easy to expose this API. You'd like to make sure it's only consumed by other developers whom you trust. You'd like an easy way to monitor and log its use. You'd like for the API to have a single, coherent way for it to know which end user is making the call. That's when you use cloud endpoints. It implements these capabilities and more using an easy-to-deploy proxy in front of your software service. And it provides an API console to wrap up those capabilities in an easy-to-manage interface. Cloud Endpoints supports applications running in GCP's compute platforms, in your choice of languages and your choice of client technologies. Apache Edge is also a platform for developing and managing API proxies. It has a different orientation, though. It has a focus on business problems like rate limiting, quotas, and analytics. Many users of Apache Edge are providing a software service to other companies, and those features come in handy. Because of the back-end services for Apache Edge need not be in GCP, engineers often use it when they are taking apart a legacy application. Instead of replacing a monolithic application in one risky move, they can instead use Apache Edge to peel off its surfaces one by one, standing up microservices to implement each in turn, until the legacy application can be finally retired.
In this demonstration, I'll create a simple App Engine application using the Cloud Shell local development environment, and then I'll deploy that application to App Engine so we can play with it. Let's start working with App Engine using Cloud Shell. I'll start by cloning the source code for a simple App Engine application from GitHub. Now that I have the source code, let's go into the tree in which it is stored. Let's examine the file app.yaml. This file specifies the configuration of the application. The app.yaml file specifies the runtime for this application, as well as handlers and required libraries. Handlers are the URLs on which it responds. Let's run the application locally here in Cloud Shell, using the built-in App Engine development environment. Now the application is running locally. Let's use Cloud Shell's built-in previewing capability to preview it. Here's a local instance of our application. It appears to work. Recall that the application is running locally here in Cloud Shell. We can confirm that by going to the App Engine dashboard. In the Products and Services menu, we scroll down to App Engine and choose Dashboard. Notice that no applications are deployed. Let's return to Cloud Shell now. We will press Control-C to abort the development server. Now we're ready to deploy our application to the real App Engine service. We're prompted for the region. We'll choose the one that's geographically close to us. We're asked to confirm the deployment. App Engine files are stored in Google Cloud Storage. Now let's go back to the App Engine dashboard. Let's refresh. There's a link to our application at top right. This is the deployed version of the application. When we're done with this application, we can disable it using the App Engine console. We scroll down to Settings and click Disable Application. We're asked to confirm the application's ID. Now the application has been disabled. In this demonstration, I created a simple App Engine application. I started off in the Cloud Shell local development environment, and then I deployed it to App Engine so we could see it in the management interface.
వచ్చానమ్మా.
People create great applications in the Google Cloud. Popular tools for development, deployment, and monitoring just work in GCP. You also have options for tools that are tightly integrated with GCP, and in this module, I'll explain them. Let's start with talking about development. Lots of GCP customers use Git to store and manage their source code trees. That means running their own Git instances or using a hosted Git provider. Running your own is great because you have total control. Using a hosted Git provider is great because it's less work. What if there were a third way? Maybe a way to keep code private to a GCP project and use IAM permissions to protect it, but not have to maintain the Git instance yourself. That's what Cloud Source Repositories is. It provides Git version control to support your team's development of any application or service, including those that run on App Engine, Compute Engine, and Kubernetes Engine. With Cloud Source Repositories, you can have any number of private Git repositories, which allows you to organize the code associated with your cloud project in whatever way works best for you. Cloud Source Repositories also contains a source viewer so that you can browse and view repository files from within the GCP console. Many applications contain event-driven parts. For example, maybe you have an application that lets users upload images. Whenever that happens, you need to process that image in various ways. Convert it to a standard image format, thumbnail it to various sizes, and store each in a repository. You could always integrate this function into your application, but then you have to worry about providing compute resources for it, no matter whether it happens once a day or once a millisecond. What if you could just make that provisioning problem go away? It would be great if you could write a single-purpose function that did the necessary image manipulations and then arrange for it to automatically run whenever a new image gets uploaded. That's exactly what Cloud Functions lets you do. You don't have to worry about servers or runtime binaries. You just write your code in JavaScript for a Node.js environment that GCP provides, and then configure when it should fire. There's no need for you to pay for servers either. You just pay whenever your functions run, in 100 millisecond intervals. Cloud functions can trigger on events in cloud storage, cloud pub sub, or an HTTP call. Here's how setting up a cloud function works. You choose which events you care about. For each event type, you tell cloud functions you're interested in it. These declarations are called triggers. Then you attach JavaScript functions to your triggers. From now on, your functions will respond whenever the events happen. Some applications, especially those that have a microservices architecture, can be implemented entirely in cloud functions. People also use cloud functions to enhance existing applications without having to worry about scaling. Setting up your environment in GCP can entail many steps. Setting up compute, network, and storage resources, and keeping track of their configurations. You can do it all by hand if you want to, taking an imperative approach. In other words, you figure out the commands you need to set up your environment the way you want. If you want to change your environment, you figure out the commands to change it from the old state to the new. If you want to clone your environment, you do all those commands again. This is a lot of work. It's more efficient to use a template. That means a specification of what the environment should look like. It's declarative rather than imperative. GCP provides Deployment Manager to let you do just that. It's an infrastructure management service that automates the creation and management of your Google Cloud Platform resources for you. To use it, you create a template file using either the YAML markup language or Python that describes what you want the components of your environment to look like. Then you give the template to Deployment Manager, which figures out and does the actions needed to create the environment your template describes. If you need to change your environment, edit your template, and then tell Deployment Manager to update the environment to match the change. Here's a tip. You can store and version control your Deployment Manager templates in cloud source repositories. You can't run an application stably without monitoring. Monitoring lets you figure out whether the changes you made were good or bad. It lets you respond with information rather than with panic when one of your end users complains that your application is down. Stackdriver is GCP's tool for monitoring, logging, and diagnostics. Stackdriver gives you access to many different kinds of signals from your infrastructure platforms, virtual machines, containers, middleware, and application tier, logs, metrics, and traces. It gives you insight into your application's health, performance, and availability. So if issues occur, you can fix them faster. Here are the core components of Stackdriver: monitoring, logging, trace, error reporting, and debugging. Stackdriver monitoring checks the endpoints of web applications and other internet accessible services running on your cloud environment. You can configure uptime checks associated with URLs, groups, or resources such as instances and load balancers. You can set up alerts on interesting criteria, like when health check results or uptimes fall into levels that need action. You can use monitoring with a lot of popular notification tools, and you can create dashboards to help you visualize the state of your application. Stackdriver logging lets you view logs from your applications and filter and search on them. Logging also lets you define metrics based on log contents that are incorporated into dashboards and alerts. You can also export logs to BigQuery, Cloud Storage, and Cloud PubSub. Stackdriver error reporting tracks and groups the errors in your cloud applications, and it notifies you when new errors are detected. With Stackdriver Trace, you can sample the latency of App Engine applications and report per URL statistics. How about debugging? A painful way to debug an existing application is to go back into it and add lots of logging statements. Stackdriver Debugger offers a different way. It connects your application's production data to your source code, so you can inspect the state of your application at any code location in production. That means you can view the application state without adding logging statements. Stackdriver Debugger works best when your application's source code is available, such as in cloud source repositories, although it can be in other repositories too. You can't run an application stably without monitoring. Monitoring lets you. In this demonstration, I'll use Deployment Manager to create a GCP deployment and maintain it. I'll also view resource usage in a virtual machine using Google Stackdriver. I'll work with Deployment Manager using Cloud Shell. For the sake of convenience, I'm going to define an environment variable containing my preferred GCP zone. I already have an environment variable containing my GCP project ID. Now I will create my Deployment Manager template using a text editor. I've created my template in another window and I'll paste it in here. Now let's take a look at what we have. This template defines a virtual machine as a resource. It's named MyVM. This virtual machine is defined to have a startup script, apt-get update, which calls for its database of applications to be updated. Be aware that the syntax of Deployment Manager requires you to specify the preferred zone in a few places and the GCP project ID in a few places. We'll substitute them into this file using the sed command. I'll write my file out to disk. Now let's use sed to substitute in our project ID. The sed command has no output when it is successful. Similarly, we'll use the sed command to substitute in our preferred zone. Let's look at the file again and see our results. Our GCP zone has been substituted into the template, as has our GCP project ID. Now we're ready to build a deployment from this template. The template will create a new deployment in Compute Engine. It'll be called My First DEPL, and it'll use the template mydeploy.yaml. It's done. We can confirm its status using the gcloud command. There's our deployment, My First DEPL. Now let's look at the resulting virtual machine. We'll go to the Compute Engine VM Instances page. There's our virtual machine, my-VM. We click on its name to open its details and scroll down, and there's its startup script, apt-get update. Now let's make a change to our template. I'm going to add a command to the startup script. This new command installs the Nginx Lite web server. Now we'll update our deployment. Now that the update is complete, let's go back to our virtual machine instance detail page. And now look again at the startup script. The startup script has been updated. Now let's put some CPU load on the VM we created and monitor it using Stackdriver. First, we'll log into the virtual machine by connecting to it using SSH. This Linux command creates an artificial CPU load on the virtual machine. In essence, it forces the CPU to continuously attempt to compress random data. Now let's return to the GCP console and set up Stackdriver monitoring. In the Products and Services menu, we scroll down to Stackdriver Monitoring. We confirm that we want to create an account. And we'll confirm that we wish to monitor our GCP project. We don't want to monitor any AWS accounts, so we'll click Skip AWS Setup. For this particular activity, there's no need to install the Stackdriver monitoring agent, so we just click Continue. don't need to get reports by email for this demonstration, so we click No Reports.
The upside of traditional IT is that the organization has a high level of cost control. The procurement and finance teams have a pretty clear idea of how much resources cost, so that costs are relatively predictable. In contrast to traditional IT,
Now we click Launch Monitoring.
resources capacity is much more elastic. There is no lengthy procurement process with a server.
We'll click Continue with the trial.
There is no need to buy extra servers to cover the spike in computing demands. This elasticity
Notice that our CPU utilization increased sharply a few minutes ago when we started our artificial load.
available when needed. Think about EKS. In addition to getting
In this demonstration, I used two GCP services, Deployment Manager and Google Stack Driver. Using Deployment Manager, I created a deployment and I maintained it. Using Google Stack Driver, I viewed resource usage inside of a virtual machine.
that you can focus better on taking care of the business specifically. Now, as a more computing, system activity also means that it is very, very easy to lose control with just overspend. Do you remember the survey findings from the previous list? Overspending creates a 30% or more estimated amount of cloud waste. Of course, many organizations, including problematics, want to get back control of their cloud spending and reduce waste while enjoying the awesome benefits of cloud computing. To control cloud costs, organizations should care about EKS costs. For simplicity, let's consider only the development and financial teams. Each team has its own perspectives and motivations. Development teams are interested in using the latest technology to avoid being left behind. For business and EKS are hospital teams.
You figure out whether the changes you made were good or bad. It lets you respond with information rather than with panic when one of your end users complains that your application is down. Stackdriver is GCP's tool for monitoring, logging, and diagnostics. Stackdriver gives you access to many different kinds of signals from your infrastructure platforms, virtual machines, containers, middleware, and application tier, logs, metrics, and traces. It gives you insight into your application's health, performance, and availability. So if issues occur, you can fix them faster. Here are the core components of Stackdriver: monitoring, logging, trace, error reporting, and debugging. Stackdriver monitoring checks the endpoints of web applications and other internet accessible services running on your cloud environment. You can configure uptime checks associated with URLs, groups, or resources such as instances and load balancers. You can set up alerts on interesting criteria, like when health check results or uptimes fall into levels that need action. You can use monitoring with a lot of popular notification tools, and you can create dashboards to help you visualize the state of your application. Stackdriver logging lets you view logs from your applications and filter and search on them. Logging also lets you define metrics based on log contents that are incorporated into dashboards and alerts. You can also export logs to BigQuery, Cloud Storage, and Cloud PubSub. Stackdriver error reporting tracks and groups the errors in your cloud applications, and it notifies you when new errors are detected. With Stackdriver Trace, you can sample the latency of App Engine applications and report per URL statistics. How about debugging? A painful way to debug an existing application is to go back into it and add lots of logging statements. Stackdriver Debugger offers a different way. It connects your application's production data to your source code, so you can inspect the state of your application at any code location in production. That means you can view the application state without adding logging statements. Stackdriver Debugger works best when your application's source code is available, such as in cloud source repositories, although it can be in other repositories too. In this demonstration, I'll use a deployment manager to create a GCP deployment and maintain it. I'll also view resource usage in a virtual machine using Google Stackdriver. Now, I'll create a deployment manager template using a text editor. I've created my template in another window and I'll paste it in here. Now let's take a look at what we have. This template defines a virtual machine as a resource. It's named MyVM. This virtual machine is defined to have a startup script, apt-get update, which calls for its database of applications to be updated. Be aware that the syntax of Deployment Manager requires